Yeah, welcome to this topology and geometry seminar. And today we have David Miyamoto from University of Queen's University, Canada, and he will be talking on diffeology. So today is the first talk, and he will give a definition and a bit of examples in diffeology. Yeah, and over to you, David.
Oh, yeah, thanks for the introduction. Thanks also very much for the invite. It's my pleasure to be able to speak here, and it's also a privilege. Um, yeah, so I guess I called this series of three lectures a first encounter with diffeology, and I expect for many of you, if not most of you, um, this would be a first encounter. Diffeology is not new, but it's something that's growing, I find, over the years. And so a lot of people see it for the first time, and I'm hoping that I can make this at least a pleasant first encounter for you. So, yeah, well, today we'll begin with definitions and examples. Um, please, by the way, if you have any questions, don't hesitate to ask them. That's perfectly okay with me. Uh, so let's begin. Oops. Uh, I thought I'd begin with this fun quote that you can find online. So this is on the NLab here for generalized smooth space, and it's so manifolds are fantastic spaces. It's a pity that there aren't more of them. And so this kind of captures the reason to look at what is diffeology. Diffeology is a generalization of manifolds. So we will try and preserve some of the tools from smooth manifolds in settings where you no longer have smooth manifolds. So I thought I'd start off from the basics. So informally, just a smooth manifold. By this, I mean a space modeled on Euclidean space. So I'll be thinking of real manifolds, real smooth manifolds for basically everything here. Um, and so we have these standard examples of sphere, tori, Mobius bands, Klein bottles. And the point is that we have a lot of refined tools to study the category of manifolds, for instance. So Morse theory, a Cartan calculus, singular cohomology, de Rham cohomology. And some of these will extend to diffeology. Oops, that's not a good color. So some of these will extend to our diffeological spaces, and some of them might extend. I mean, this is sort of would be work in progress to do this. For example, for Morse theory. Okay. And there's also many geometric structures we can put on manifolds, like Riemannian metrics, symplectic structures, foliations, etc. And again, uh, we would aim to maybe put some of these on diffeological spaces. But before I keep saying diffeological spaces, let's get a sense of what I mean by not manifolds. So here's the type of non-manifolds that we're going to encounter. Um, so the arbitrary quotient of a manifold, for instance, can fail to be a manifold. An arbitrary subset can also fail to be a manifold. And if you have two smooth manifolds, then the space of smooth maps between them might not be a manifold. And I mean, basically, it's never a manifold, by which I mean never a finite dimensional manifold. Of course, in any of these three situations, quotients, subsets, or mapping spaces, they could be manifolds. But the point is that they're not in general. So diffeology will generalize manifolds in a way that handles these situations sort of without condition. So any quotient of a manifold will be a diffeological space, or any subset will be. And then the question is not so much whether you have the smooth structure, it will be what can you say about the smooth structure that you're given by diffeology. And also in the next talk after this, we'll introduce a different viewpoint, so higher geometric structures and infinite dimensional structures. And then we'll discuss how this diffeology can relate to those. But today we're focusing on diffeology. So here, just to get ourselves grounded, are some, I think, hopefully not too complicated examples. Um, so we have the orbifold, the cone, and so this is obtained by taking the plane, which you can view as C, if for just to make it easier to write down the group action, the plane quotiented by the cyclic group of order K. So this ZK here is a cyclic group. And the action is going to be rotation by 2 pi over K degrees, radians. And this is the state base that we should expect to get. So we take the plane, we cut out a triangle and glue that triangle, the edges that we cut out, and we should get some kind of cone shape. The problem, of course, is that that's not actually what it looks like, in the sense that topologically, this is just R2 again, right? So I can flatten this cone down, and the singularity that seems to be there will go away. And in fact, topologically, the singularity was never there in the first place. These are all homeomorphic to R2. So that's what this top means. It means homeomorphic. Or in other words, isomorphic in the category of topological spaces. Um, but we would, want to say maybe that you have a cone point there, and we see that if you try to put a smooth manifold structure that seizes this cone point, then it's not a quotient manifold. In other words, the map that goes from this R2 to R2 to CK, the quotient map from R2 to CK, even if topologically these spaces are isomorphic, the map cannot be viewed as a submersion. So that's what I mean by not a smooth quotient manifold. I mean that the quotient is not a submersion. And that's quotients. We also take subsets. So here's a subset that appears in maybe algebraic geometry, which would be zero sets of polynomials. So this one is called the semi-cubic, and this is a subset of the plane with the equation x squared equals y cubed. So the zero set of x squared minus y cubed. And it looks like this. We have the cusp here, sorry. And of course, again, topologically, this is just homeomorphic to R. And this is because the map the map T maps to T cubed, T squared here is a homeomorphism. Cubed root, taking the cubed root of something is still a homeomorphism, even if it's not a diffeomorphism. So topologically, we have R. And on the other hand, though, there's a cusp, and so this is not an immersed submanifold, right? So the tangent at the origin of this cusp fails to exist. Okay, so here's a subset that's not an immersed submanifold. And finally, just to remind you, the set of smooth maps between manifolds, I'll denote it as C infinity Mn. And by smooth, I really mean infinitely differentiable. And here, I'm not going to try to make a picture of these. If someone has one, I'd like to know, because the problem is that these are highly infinite dimensional. Unless, of course, M is a finite collection of points or something. But let's assume that M is not a finite collection of points. Then these are infinite dimensional. And so to be infinite dimensional, the definition could essentially be not finite dimensional. But in certain situations, we do have some control over that infinite dimensionality. So topologically, if M is compact, for instance, if the domain is compact, we can equip this with the structure of a Frechet manifold. So you would have local neighborhoods, and the local charts would go to some Frechet manifolds. But that's only if M is compact. And in any case, it's still infinite dimensional. Of course, M could very well not be compact. I mean, it could be the plane or a real line, and then already this space would not have a natural Frechet structure. By natural Frechet structure, I mean a Frechet structure where, for example, you might have some exponential law holding, and we'll see, but we'll talk about the exponential law in the future. So if M is not compact, this is not a Frechet manifold, and in fact, the ways to treat it as an infinite dimensional manifold give some maybe unexpected um, results. Again, we can talk about this more in the next lecture when we will discuss infinite dimensional manifolds formally.
So here,
Okay.
even if we do CKMN, that's also has the same result.
CK?
Yeah.
No, so CK will be at least, so this will be Banach then, if M is compact, if I'm not mistaken. So the Frechet here is coming from the infinite derivatives that we take. So we need infinite semi-norms to capture convergence, one for each convergence in the first derivative, second, third. So when you have CK, you can bundle, there's only finitely many, so you can basically create a norm that captures all the finitely many degrees of convergence that you want. But then if M is compact, then I think that you don't have to worry about what's happening on the base. So you only have the derivative directions to take care of. See this. But if M is non-compact, then I think that CK is possibly Frechet. Uh, yeah. The non-Frechetness is really characteristic of having infinity here. Does that help?
Okay. Okay. Yeah. Thank.
Okay. So now I haven't even told you what diffeology is. I've told you what it might try to do,
And
but I haven't told
also,
you what it is.
sorry.
Oh, yeah.
Uh,
Yeah.
yeah. So in here, if M and N both are compact, does the structure get more simplified or something?
So n being compact to me doesn't I don't really view it helping much, like in terms of making the structure easier. Um, yeah, yeah, n being compact
Okay.
doesn't make much of a difference unless n is finite or something. But even if n is finite, then yeah, then I guess you just have a finite set. So yeah, this finite n, sure, things get simpler. But for example, putting n to be the circle or something like this
Mm.
doesn't really reduce the difficulty too much. For
Okay.
example, this failure to be Frechet. So for example, already this thing is is already not naturally Frechet.
Right.
Um, there are so what could make n easier is if n is if you're looking at sections of a vector bundle or something. So maybe then you don't
Mm.
have, yeah. So if n, for instance, is Euclidean space, then you do have uh, Frechet structure. So I really should also put here not generally a Frechet manifold. There will be situations where M, the domain can be non-compact and you can have a Frechet structure, but in complete generality, there's not one structure that covers all the situations. Okay.
Okay.
Yeah, thanks for the question. So yeah, so I didn't tell you what diffeology is, but already with these examples, I hope I can at least give you a beginning sense of what it does. So here we could summarize what diffeology will see. So if I have the orbifold cone, the CK, where I did a quotient of the plane by the cyclic group, then topologically this is R2, but diffeologically, the natural diffeology on these spaces will see the angle. So they will not be diffeomorphic if K does not equal L. If K equals L, it's the same set, right? It's the same space. But diffeology will see the precise angle that you are quotienting by, which is what we wanted, right? We wanted to be able to distinguish the cone points at all. So for instance, none of these are the plane either. They're all distinct. So we can see a singularity at the origin, and we can actually see, again, the sort of how tightly you wound the cone. Um, the semi-cubic, now this one is a bit interesting and maybe goes against what the first intuition you get from the first line. So topologically is R, and diffeologically actually is also R. So Diffeology equips the semicubic with a smooth structure, the smooth structure of the real line, and it does not see the cusp. So you have a manifold, but you actually fail to see the singularity. Um, so I will talk about more about that in a bit. Um, and finally, for the function spaces, so here, I mean, in this small table, I just put it's subtle. I don't have space to put in the whole discussion here. But diffeologically, you can treat these in a much more uniform way. So they're all diffeological spaces in all sort of the same way. And for instance, we can make some statement like this, the tangent of the space of smooth functions, which exists in diffeology, is the space of functions into the tangent of n. Um, and this kind of to motivate this statement why one so the point here would be that we can rigorously say something that someone might expect a little bit to be true is that if we had our single smooth function, so maybe I'm taking a base point at f, then what does it mean to move tangent? Well, it kind of means to move to perturb it, right? So I take a little perturbation of my function. I'm trying to test, maybe I start perturbing it down here a bit. I take a little perturbation, and then essentially I want to take my, I want to take d by dt over to zero. So take t to zero. And what this will do is we'll see that we're kind of moving the function in the tn direction, right? So this is why one might think that the tangent should be smooth functions into the tangent bundle. And in fact, it is diffeologically. Without a smooth structure, we could not say what this symbol even means here. Okay. And another example, which I think is one of the more famous ones for diffeology, and really this is one of the springboards that kept people interested in diffeology, is the irrational torus. So for an irrational number, alpha, I can act on the real line by the subgroup z plus alpha z. So this is an abelian subgroup of the abelian group that is R, and I could take the quotient. But a more geometric way to see this quotient is by a torus quotiented by the line of slope alpha. And diffeologically, these are going to be the exact same space. And here is the space. So this is not the quotient itself, but this is the thing you're quotienting by. So the red and blue segments are single connected curves. So I fix my angle alpha, I travel up, and I travel up. And because I'm on the torus with these identified, then I'll come back, when I hit the top, I'll come back down. And then when I hit the side here, I'll come back here. And I use blue just to distinguish the fact that we've gone around, once or something. And then we come back around. So I just keep doing this. And because the angle is irrational, this single curve is going to be dense in the torus, right? So we'll have a dense curve in the torus. It won't hit every point, but it will be dense. Then if I just shift my starting point a little bit over, I'll get a different dense curve. By translating it parallel to itself, I get a partition of T2 into these dense curves. In other words, a foliation of the torus. And the quotient space is the irrational torus T alpha. So T alpha is the quotient space of this. And because a single leaf of the foliation, a single equivalence class of the relation is already topologically dense in the torus. Similarly, z plus alpha z is dense inside R for irrational alpha. The quotient space will have trivial topology. The only two open sets will be the whole thing and the empty set. And this doesn't matter what alpha is. As long as alpha is irrational, I always get trivial topology. But diffeologically, I actually have some more structure. I can see some more geometry. So these two irrational tori will be diffeomorphic diffeologically if and only if alpha and beta are related by what could be called an integral homography, I think. So what I precisely mean is that is this here. So alpha is A beta plus B over C beta plus D, where ABCD is an element of GL2. Um, so not all irrational tori are diffeomorphic to each other. There's diffeomorphism classes, and they kind of distinguish the angle alpha, at least up to these homographies. And in particular, then they can't be trivial because all the trivial things would be isomorphic to each other. So none of these spaces are trivial spaces. Um, and this relation actually appears again in C-star algebras for the irrational tori there, and in Lie groupoids for the Lie groupoids representing these irrational tori. So this is also a meaningful relation that appears elsewhere, and we'll see that in the future. Okay, so this and we see this result is from 85. Well, in the next slide or so, we'll see that diffeology itself was created in the 80s. So this came fairly early on, and it's one of the things that keeps it relevant today because these irrational tori are relevant. We'll see how they come up in the future. Okay. So that is my intuitive, hopefully intuitive introduction. And so now we will work towards the actual definition of diffeology. So I want to remind a more precise notion of smooth manifold. So a smooth n-dimensional manifold structure is determined by the charts. And actually, I guess I should say local parametrizations because I'm going to take my charts to be from Euclidean spaces into M, but it's a bit semantics. So here my charts will be from open subsets of Rn into M. And then I take a maximal atlas, and that will be my manifold structure. And so the charts are giving the local model. So the image of a chart is identified with its domain. And we say that's what we mean by, locally Euclidean. But they also give us, incidentally, the smooth maps into the manifold. So the charts let us talk about the smooth curves, smooth homotopies between curves, maps from R3 into M, etc. And typically we see that this one implies this one here, right? The local model tells us what smoothness means because we sort of we have some notion of smoothness on Rn, which is uncontested notion of smoothness. Every derivative exists. There's no question there. And so on a manifold, we use that to define smoothness on the manifold. But diffeology is going to remove the first feature because, as we saw, all of those spaces before are not going to have local models. And we keep the second. And in fact, we upgrade the second condition here to the definition of the structure. So the nature of a diffeological structure is going to be the data of the smooth maps into the space. And we will no longer require local models of our space. I mean, already for the irrational tori, their quotient topology is trivial. So what could a local model look like? It would have to be something defined on the entire torus, and we're kind of already lost. So yeah, here's the formal definition. So again, a little historical remark. This goes back to Soriot, Jean-Marie Soriot in the 80s. And so this is one of the first papers he wrote here, there. But the notion or the idea of generalizing manifolds in this way was not entirely new. So K.T. Chen had his own notion of he didn't call it diffeology, but his own generalized notion of smooth manifold. And the difference here is that we will see that sort of Soriot uses open subsets and Chen used convex subsets. Now, what do I mean open or convex? Here's where these come in. So a diffeology on a set X is an assignment that sends each open subset of Rk for each k to a collection of maps, which I'm denoting D sub u. These are supposed to be thought of as the smooth maps into X, and we call them plots with the three conditions. So the diffeology is the assignment, the data of the assignment, and the conditions are that for every u and every k, or for every k and every u inside Rk, the constant map has to be in there for each constant map. So, a constant map would be R maps to X for a fixed X. Each of those has to be inside my assignment. In other words, constant maps are smooth always. A pre-sheaf condition. So again, we know what it means to be smooth between open subsets of Euclidean domains. So this notion here does not need really definition. Every derivative exists, is what I mean. And if I have a known cheese map, then when I pull back the plots on U, I have plots on V. In other words, smoothness is preserved under pulling back by known smooth functions, smooth maps. And finally, a sheaf-like condition. So if I have a given map from an open subset into X, and at each U, I have a neighborhood where I'm actually a plot. So F restricted to U prime is a plot of X for each U prime. Then F itself was a plot. And this last one can be thought of as smoothness is a local condition. If I have a given map into a manifold, then I can check if it's smooth by looking locally. Is it smooth in each neighborhood of each point? Then it's smooth on the whole domain. And it's here, that's what this sheaf condition is saying. Uh, the fact that I labeled these as concrete, pre-sheaf, and sheaf is not an accident. So the data of a diffeology is, or rather a diffeological space identifies with a sheaf. A sheaf on the site of Euclidean spaces. So this is not something I wrote down, but right here. So, or a diffeology corresponds to a sheaf on the site of Euclidean spaces. So the objects are the open subsets of Rk for all k. So it's not a sheaf on some subsets of a manifold. It's not a sheaf on any given manifold. This is a sheaf on the collection of, the site is all collection of open subsets. And the morphisms are the smooth maps between them. So this
So
is another way to view a diffeology. Yeah.
one question I have. So so essentially this diffeology we can think of as a graded object, right? So it's
Um,
graded over K. So graded sheaf. For every RK, we have a sheaf, and then we take this a graded set, graded kind of sheaf. And what is the so first of all, is it true way to think of it?
um,
Right way to think of it, or no? I'm doing some mistake.
so I think it's not wrong to think of it as a bit graded in the sense that it's sensible to talk about all the plots with domain K. Yeah, so I can restrict this sheaf to open subsets of a single RK, and I can talk about the plots with those domains inside RK. Um, this can lead to the notion of dimension of a diffeological space. Uh, but I think that it's not fundamental to the structure. Uh, so I wouldn't say that the
And
grading is something that we see most of the time, but it does appear. Again, you can define dimension of a diffeological space. That's going to kind of speak to some kind of grading. But yeah,
if that is the case, then uh, uh, is there any kind of compatibility condition? Like if I take RK sitting inside bigger RL,
yeah,
let's say,
yeah, yeah, yeah,
in a natural way. Okay.
yeah,
So
yeah,
that means okay.
yeah, this way.
Okay.
Yeah. So here, yeah,
Essentially the thing. Okay. So I see. Okay, I see. Hmm.
yeah, yeah.
Okay.
So yeah, so this one here, V can really be inside RK. Oh, sorry, that's illegible. This can be inside RK, and this can be inside K prime. And there's no condition on K and K prime. Um, yeah. Which does raise the question of like when I say it's a sheaf, I need some kind of topology, right, to
And
discuss the sheaf condition. There's a growth unique topology on this site that lets you do that. Yeah.
okay, I see. Okay, I think actually I don't know. I never kind of encountered this diffeological thing, but
Yep.
I encountered something called free set, free topology, and kind of non-commutative free functions, and
Hmm.
their things are like almost like that, except that at every grade they are not essentially sheaf. But okay, so I'll talk to you
Okay.
later.
Okay.
Probably there might be some connection with that.
Yeah, yeah. I haven't heard of that, but I know that diffeology at least has some applications in like Kahn's version of non-commutative geometry.
Or is
So yeah. But yeah, I'd be happy to hear more about that. Because I've never heard of that notion. Um, okay. So yeah, so here's the data for diffeology. So for each open subset of each RK, I give you the collection of plots, the smooth maps. And it's really important that we go over all K. For a manifold, I can fix K and give you the charts. For diffeology, I need to go over all K. Um, and so there's a way to view it as a sheaf. We could also just view it as a set of plots by just taking the union of all the plots and say that's a diffeology. Okay. So Chen here used convex subsets instead of opens. And then he had a notion of smooth map from convex subsets. That's a difference there. And yeah, so it doesn't hurt to dwell on this a bit. Again, the structure is going to be the maps into the space, which I guess makes this kind of a covariant framework. Um, and there's a bit of asymmetry in the definition, right? Our data is things into the set, not things out from the set. Now, that's the objects of a category. So we have a category of diffeological spaces by saying that a map is smooth. So smooth is to say a morphism in diffeology. We call them smooth if it pushes forward plots to plots. So that would be every plot in dx gets pushed forward to a plot in dy. So we can use the plots to define smooth maps between diffeological spaces. And so we have a category of diffeological spaces. I guess if you define diffeology as a sheaf on the site of Euclidean subsets, then it's immediately a category because a sheaf, the category of sheaves, basically. Now, this is again, this is the big point to consider this is that it's a complete, co-complete, and locally Cartesian closed category. In other words, it's a quasi-topos. And if those words are meaningless, then specifically what we get is that every subset and every product of a diffeological space inherits a natural one, diffeology. Quotients and coproducts inherit natural diffeologies. And the slice categories are Cartesian closed. So the mapping of space objects have natural diffeologies, which satisfy some exponential law. In other words, everything that I mentioned up to now is naturally diffeological. Um, and again, you could get this consequences from the fact that it is a sheaf on a site. That the data of a diffeology is a sheaf. And as a first example, manifolds. Every manifold is a diffeological space. So when we view M as a diffeological space, I have to tell you what the plots are on each open subset. So for each U inside some RK, the plots are those maps which are smooth in the usual sense. And here, usual sense, I mean like use the definition of smoothness on the manifold to define this collection in the first place. That collection will be a diffeology on M. And when you view M as a diffeological space with this diffeology, you don't get any more smooth maps. In other words, the functor from M to dm here, sorry, this really should be M viewed as a diffeological space is full and faithful. So there's no new notion of smooth map when we look at manifolds. This is why this makes diffeology an honest generalization of smooth manifold. It doesn't create new things when you already have finite dimensional smooth manifolds. So that's I guess manifolds in our first example. Um, And when you've equipped them with the diffeology, it looks like you forget the dimension a little bit, right? Because the data is all these smooth maps for any k. But you can recover the dimension by looking at some sort of supremum over collections that generate the diffeology, whatever that means. So the dimension can be recovered, but it no longer becomes part of the fundamental definition. Now, sometimes I think topology can help us visualize a space. So every diffeological space, which observe the set X does not come with a topology in the definition. It's not a topological space with some data. It's a set with some data. And there's some topology in the domains of the plots. I mean, these have to be open subsets of Rk. But X itself does not come originally with a topology. The diffeology comes first, and you can get at the topology later. So I can take the finest topology, which makes all the plots continuous. Finest would also mean here, like largest. The most open subsets. The more open subsets I add, the harder it is for a map into the space to be continuous. So I want the most I can possibly add while each plot remains continuous. This is called the
Sorry.
D-topology. Yeah.
So the very first example that you gave where
Yeah.
on R there was an action of on R2 there was an action of cyclic group. So in
Yeah.
general, also if I consider any Orbi fold,
Yeah.
will it be a diffeological
Yes.
space?
Yes. Yes. So that's actually a slide in a bit. Every
Okay.
orbifold is naturally diffeological. Yeah. And in fact, yeah. So I'll say that when I get to it. Good question. Okay. Yeah. So we have the D topology, and this functor has a left adjoint, or is left adjoint, has a right adjoint. I always get this confused. So given a diffeological space, I get a topology called the D topology. The functor that does that is called D. Maybe a bit confusingly, but that's just what it's called. The continuous diffeology functor is called C. So this is going from topological spaces to diffeological spaces. And you can define a diffeology by saying that my smooth maps are the continuous ones. So for each open subset U, these continuous maps are the plots of my topological space T. So here the underline denotes take the maps in the category topological spaces. And that is a diffeology, the so-called continuous diffeology. It's a rather mysterious object, but it does serve as a right adjoint to D. Because D has a right adjoint. Oh yeah, so sorry. So this the functor D is faithful. So something that's smooth will also be continuous with respect to these underlying topologies. And if I take a manifold and I take its D topology, then I will recover the manifold's topological structure. So the D topology is compatible with the notion of manifold. And so there's going to be two extremes that help ground us a little bit in diffeology. So every set consists of two distinct diffeologies. Okay, every set with more than two elements, let's say. The first one is that for each U, I can consider only locally constant maps to be smooth. So one can check that this satisfies the three conditions, and therefore I have a diffeology, and the only smooth maps from Euclidean spaces will be constant, essentially, locally constant. This is called the discrete diffeology, and the D topology of this diffeological space, X equipped with this diffeology, is discrete. Everything is open because the plots are all locally constant, so it's very easy for the pullback to be open. They're just constant maps. So every subset of X is open. In other words, the topology is discrete. So that's one diffeology, the discrete diffeology. And then there's also the coarse diffeology, where I do the other extreme, where I take everything to be smooth. Every map into X is considered smooth map. Then I have the coarse diffeology, and the D topology is coarse. So the only open subsets are the whole space and the empty set. So I guess discrete diffeology has the fewest plots possible, and the D topology has the most open sets. The coarse diffeology has the most plots possible, and its D topology has the fewest open sets. Every other diffeology sits between these. So now we will go over some of the examples in a little more detail, quotients, subsets, and function spaces. So the quotient always has a natural diffeology. And if you unwind what this would be, it's as follows. So this map is a plot if at every point I can find a local lifting along the quotient map pi. So that's what this diagram says. Every plot has a local lift. If I change R, I might need different Qs to lift my plot, but in any case, I can at least lift it in every neighborhood. Or sorry, I can lift it in a neighborhood around every point. That is my collection of plots, and that's the quotient diffeology. Here's what I was about to say earlier. The functor D is a left adjoint functor, so it's compatible with co-limits. Quotients are co-limits. So what happens is that the D topology of the quotient space is the quotient topology. So for example, the cone has a quotient diffeology. Here are the plots of the cone. It would be anything that locally lifts to R2. And the D topology of that diffeological structure is going to be R2, I guess. The underlying topology of the cone. It'll be the quotient topology, so R2 in that case. I can put that here. So D of the cone is the topological R2. But of course, as a diffeological space, it is not R2. Right? They're all distinct as diffeological spaces, even though they have the same topology underneath them. And I just wanted to give a small example of how diffeological arguments work. So already we can do something interesting in diffeology. So take two irrational tori. If I have a diffeological diffeomorphism, a smooth map with smooth inverse, then I will get a plot by pulling back by the projection of the domain. So it goes from R to TB. Remember, a smooth map from a Euclidean space is necessarily a plot. So I have a plot. The quotient diffeology says that my plot has to admit a local lifting here to F along pi b. So I get the local lifting. And so it's local, so this is a subset of R. And then I have this commutative square. And one can show that the only way to have this commutative square with this map being invertible, in particular, this map will also, the inverse will also have a lift here. The only way to have this commutative square actually is if F is an equivariant embedding. This is a non-trivial thing, and I'm not going to go into it too much, but this is the point, is that this lifting exists if and only if F is an equivariant embedding. And then that exists if and only if alpha and beta are related by an integral homography. So I'm burying the lead by must be, this buries the lead about the difficulty, but the strategy hopefully is a little bit clearer of what you now try to show. So you try and show this. Okay, so that's diffeology at work a little bit. This non-triviality of the irrational tori. And then a question about orbifolds. So every orbifold is naturally a diffeological space. In fact, I can define orbifolds as a diffeological space that is locally diffeomorphic to these quotients where gamma is finite group. In diffeology, these are all diffeological spaces. And then I can take my diffeological space X. I can just ask that it's locally diffeologically diffeomorphic to these R and mod gammas, where maybe gamma can change as I move around X. And that will be an orbifold. And if I make this definition, then the usual category embeds into diffeology. So diffeology completely contains orbifolds, and at least orbifolds as the classical Satake sense, or Thurston. Yeah, the question for groupoids is a bit different, but let's not talk about that for now. So the usual category of orbifolds embeds into diffeology. These quotients, by the way, these irrational tori, these can be called quasifolds, where if you just replace the word finite with countable here, you get what's called a quasifold. And these also embed in diffeology. I mean, these are actually maybe easier to define without any other structure, just as diffeological spaces. Okay, so this is what I wanted to say about quotients. So we saw that every quotient space has a diffeology. I told you what it is. And the irrational tori and cone orbifolds are good examples. Subsets are also naturally diffeological spaces. So again, I can tell you the diffeology. So here, I guess this would be like du. If I have a subset of a diffeological space, then the diffeology on the subset consists of those maps, which are smooth into the original space. That's what my plots are. It's a bit maybe easier to write down than the quotient one. There's no lifting condition. I have a map into A and I view it as a map into X. If it was smooth into X, I consider it smooth into A. And in this case, because of this asymmetry of diffeology, we define it using maps in. It induces the asymmetry that this functor D is not compatible really with subsets. So in general, the D topology of a subset is not the subset topology. Q is a good example. So Q sitting inside R does not have discrete subtopology. Rational intervals are open. Singletons are not open in this subtopology. On the other hand, the subdifeology is discrete. The only way I can have a smooth map into R with image inside Q is if P is locally constant. As soon as it's not constant, I'll get irrational numbers in the image. So the subdifeology, those smooth maps into Q, which are smoothest maps into R, is discrete. So the D topology is discrete of the diffeological structure. And if that's a bit wordy, the motto is that topological discreteness is always weaker than diffeological discreteness. So to be diffeologically discrete, more things are diffeologically discrete than topologically discrete. Q is an example. Z plus alpha Z, for that matter, is another example of a diffeologically discrete subgroup of R. And here's what I said about the cusp. So an unintuitive fact is that this map here is a diffeological diffeomorphism. This is a parameterization of the cusp. And the reason this is true is equivalent to the fact that a function is smooth if and only if its cube and square are smooth. Of course, only having one of these is not enough, right? Squaring the function is not enough to get smoothness. And if the cube is smooth, I could have cubed this cube root. So again, that's also not enough to get smoothness of F. But if I have both of them, then F itself is smooth. The fact that 2 and 3 are coprime is not a coincidence here. That's part of the mechanics to prove this. So I could have really put any coprime numbers here, but 2 and 3 suffices. And this theorem is a theorem of Joris, which is highly non-trivial to prove. There's a few different proofs in the literature of this, but it has a diffeological consequence, which is that this cusp actually is diffeomorphic to R. So this is a surprising fact to me. Well, I don't know. It's hard to prove this fact. And the cusp is not normally something that we think of as a submanifold. So we normally maybe think of a figure 8 as a submanifold. But here, actually, in the subdifeology, it's not. So if I parameterize the figure 8, say like that, with these open ends, I can get a diffeomorphism to R. But as a subset of the plane, it has its own diffeology as a subdifeology without any parameterization. And that subdifeology is not going to be diffeomorphic to R. The subdifeology really sees this crossing here in the figure 8. And so we can actually make some definition if we have a subset of a manifold. Because we have this weird distinction of the subset S, which is diffeomorphic to R, and the figure 8, which is not diffeomorphic to R. but yet is an immersed submanifold. I can equip it with a parameterization that makes it diffeomorphic to R. We can formalize this distinction. So if I have a subset of a manifold, I can call it a diffeological submanifold if, with its subdifeology, it's locally diffeomorphic to some fixed Rn. That's a definition of a manifold, locally diffeomorphic to Rn. And then this would include the cusp, for example. And if we wanted to not include the cusp, because this is a strange thing to have as a manifold, we can say it's weakly embedded if the inclusion is an immersion. So this includes the cusp, and this, of course, does not include the cusp, because the inclusion will not be an immersion, even if the cusp is diffeomorphic to R. And some examples of weakly embedded things, so the leaves of a singular foliation are always weakly embedded. In particular, the orbits of that action on the torus that we saw are weakly embedded. So they're dense winding inside a torus, but they are perfectly good weakly embedded submanifolds. And the figure 8 is not weakly embedded because it's not diffeological as a submanifold. It depends on the parameterization I chose. The manifold structure depends on the parameterization. It's not intrinsic. And so I think if orbifolds are sort of the more familiar object for quotients, manifolds with boundary are the more familiar object for subsets. So a manifold with boundary is a diffeological space that is locally diffeomorphic to the half spaces x1 to xk bigger than 0 inside Rn. Maybe I should put maybe n minus 1 if I like. And if you have the usual category of manifolds, it embeds into diffeology fully faithfully. So you don't get any spurious smooth maps between them, and its diffeology gives sort of a uniform way to talk about them. Instead of having to construct manifold with boundary charts and talk about specifically smoothness between those things, the ambient category diffeology gives us a setting to say a manifold with boundary is locally diffeomorphic to a half space. The smooth maps are built into the structure already then. We can also then define manifolds with corners as well. Okay, and that's what I wanted to say about subsets. So the D topology is not quite compatible, or it's more subtle the compatibility because, again, it's a left adjoint and not a right adjoint. So subsets are examples of limits, and right adjoints would be the ones that are compatible with limits. Manifolds with boundary are examples. And finally, we have the functional diffeology. So the functional diffeology, I have to tell you what the plots are. And so what is a plot from U? So P here, I use the notation R maps to P sub R. And this will be considered smooth if this adjoint sort of map is smooth. So if I uncurry the map, so U times X to Y, then I can take the pair Rx. PR is a function from X to Y, so I can plug in X and I get an element of Y. This map needs to be smooth. And that is the data of the functional diffeology. So one consequence of this is that if I take some arbitrary diffeological space, X, and I ask what are the maps from X into the mapping space, then these will be isomorphic as diffeological spaces, which you can really, maybe you can see it already from the definition of plot, right? It's kind of built into the definition of plot. And this is the exponential law. Which is what makes the category Cartesian closed. So this fact being true is what it means to be Cartesian closed, and what it means to contain function spaces. When you put infinite dimensional manifold structures on these, even outside diffeology, this equivalence is desired. Like, everything can be a Fréchet manifold if I equip it with some trivial structure. But we're really trying to get these exponential laws on these mapping spaces when we equip them with smooth structure. So diffeology will always have it. And in some cases, you can get a Frechet structure that also doesn't. So this is a functional diffeology, and that's Cartesian closeness. This was Chen's original motivation. So Chen wanted to do some path integrals, and so he wanted to functional diffeology on path space. Now, implicit here, I'm using something I didn't define, which is a product diffeology, right? So we're saying this map is smooth, but X is a diffeological space. So already, like, what is a diffeology on the domain that I'm using? And I'm using the product diffeology. So if I have some product of spaces, the plots are those maps into the space. The underlying set of the product is the Cartesian product of sets. So a map will be a sequence of maps here, one for each alpha. And I just require that each member of the sequence is a plot of each X alpha. So this is a product diffeology. And using the functional diffeology, we, for example, have a diffeological structure on diff M for any manifold M, compact or not, by giving it this substructure from that mapping space. And this is a diffeological group. So one can show that the inversion is also smooth. And that was Suryo's original definition. He wanted to capture these diffeomorphism groups without so much functional analysis. And we also have section spaces as a sort of example appearing in nature. So if I have a map, I can take the space of sections of the map. I guess if it's not surjective, this is empty. So let's think of pi as a submersion or something. A surjective submersion. So I have the space of sections. And I give it the subdifeology from its inclusion in that space. If V is a vector bundle, then this thing has a usual Frechet structure, and I can recover the Frechet structure by taking the D topology. So I take the D topology of the diffeological space of sections, and I get its usual Frechet vector space topology. That's a Waldorf there. Although possibly this is, I think Waldorf wrote down what people might have known informally. If I have a fiber bundle over a compact M, then again, I get the usual manifold topology on the space of sections. So diffeology is agreeing when the Frechet structures exist, we're getting them back. But in complete generality, for any M, for any F, this does not have some canonical Frechet structure. And so that's what I was saying earlier about the function spaces with M non-compact. In complete generality, this will not have one, but it will always have diffeology. And so this could be a natural stopping point. And I think, yeah, so the rest of the slides here are just about some structures on diffeological spaces, but maybe I'll end here and then I'll let that be for questions. So yeah, thank you.
Yeah. Okay, so I have one question. So, like, there are a bunch of examples, but can you give a non-example? Because I didn't find any non-example in your slides, at least.
Yeah. So a non-example is kind of hard for me to think of what that could be. So I guess, yeah, it's sort of have to think of what we mean by a non-example, because the thing about diffeology is that if I have a given diffeological space, subsets, quotients, function spaces will all have diffeologies, right? And I can also equip every set with some diffeology. I can always equip it with the discrete diffeology, for example. So it's kind of like, it's a bit like looking for a non-example of a topological space. So what we would be looking for maybe is a space that does not seem to have a natural diffeology, right?
Yeah.
So maybe something like bornological spaces where we sort of have a system of bounded sets.
Uh,
So it's a bit like X with some bounded, that this is the data of a borderlogical space is X with a system of bounded sets. Maybe this, it's hard to say what a natural diffeology would be, you know,
okay.
because like, I would need to then like, so then what would be du? See, I can't say this would be maybe a natural guess for my plots on domain U would be the collection of bounded maps into X, but that is not a sheaf because locally boundedness is not a local condition. Um,
Mhm.
right. So I could be locally bounded and not be globally bounded. So this would be, I guess, maybe an example where you have some structure that's a bit geometric in some way, but it's not clear what the natural diffeology is on it.
I see.
Yeah.
So in particular, in that note, in particular, if you have any pre-shape which doesn't have shape structure, will maybe give
Yeah.
you a kind of
Y-
non-example.
Yes. Yes. Yeah. Any pre-sheaf that's not a sheaf, you can get a non-example. Um, that actually brings to mind another good non-example. So if you say, yeah, diffeology is really sheaf on the collection of open subsets. Well, here's a sheaf on open subsets, um, which is the Durab sheaf. So this sheaf, it actually satisfies the sheaf condition, but this is not a diffeological space. And the reason for that is that I said they correspond to sheaves, but there's this one condition that sheaves that's a bit less natural for sheaves, which is the concreteness condition, which is to say that the constant maps are plots. And the constant maps are plots. What that means is that you have an underlying set, and then you really have a structure on a set. And without that condition, you can have something like the Durham sheaf, which is not a diffeological space because the underlying set is a bit unclear, right? Um, this sheaf, the underlying set of this sheaf is a point, and it's not a structure on a point. So, uh, yeah, not a diffeological space, and it's because it's not so-called concrete. And if I want to say diffeology corresponds to sheaves, I should say so-called concrete sheaves. But I don't want to get too much. I didn't want to get too much into the notion of what a concrete sheaf is because one of the advantages of diffeology is that I could define it without sheaves and still have a sensible thing to talk about.
Okay. So, are there any other questions? Okay, so if not, then that's thanks to David, and we'll meet again at the same time on next Wednesday. Okay, yeah.
Yeah, thank you.
Sorry, next
Thank
Tuesday.
Yeah.
Yeah. Okay, bye. And could you please share the notes after that so that I can put it on the website?
Yeah. I can share these. I can share them with the annotations too.
Sure.
But I'll share whatever. Yeah. I'll share everything.
Okay, yeah. Thank you.